Chamfers are hard. Let me explain. On our Fjell blade, when we make this blade, we call this a soft blade because we machine it when it's soft. We want a tiny little chamfer on the top and a tiny little chamfer on the bottom. The problem with that is that when you're trying to do the same tool, because I don't want to flip over the part to chamfer both sides, I want to try to do everything from one fixturing. When you're trying to use one tool to cut the top chamfer and then come underneath and use the bottom chamfer, there are so many variables, and the more I get deeper into my manufacturing journey, the more I realize how many variables I wasn't even paying attention to before. So in this video, real quick, we're going to deep dive into a bunch of those variables. Under our Zeiss microscope, I want to show you guys what I'm talking about. So for example, this is a nice little chamfer. Beautiful, crisp, even, consistent. Oh look, this side even has one too. Kind of good, right? Wrong, because if we trace this chamfer, we notice that it gets bigger and bigger and bigger around the back end of this knife. And then if we flip it over, whoa, where's my chamfer? Why are you not there? Or chamfer for some of you fancy people. So this chamfer, look, it's getting bigger and bigger on this side. And then if we flip it over to here, it's gone. And then it starts leading in, comes into pretty much the size that I want, and then gets fatter and fatter on this side. So basically, I'm showing you this chamfer is all over the place. Why? Why is that? I actually scratched my head for a while in this one because, as I said, there's a lot of variables. And it's super frustrating. So when we made the first 100 Fjells, this came up. This came up quite a bit, and it's very frustrating to solve. We can comp the tool, we can make it shorter, longer, but every blade seemed to be different, and there were other things too. So, okay, let's go through one by one. Variable number one. Grab this. Variable number one is mostly solved by this guy, our Okamoto ACC 1224 SA1. This is a very beautiful, very nice Japanese surface grinder. Magnetic plate, chuck, that is an electromagnet. So you put your blades on here, you turn the electromagnet on, this big spinning wheel, grinding wheel, CNC controlled, choo, 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 choo. Our beginning stock, here's a Fjell, no, that's a Rask. The beginning stock looks gross and thick and has that kind of mill scale grossness to it. They're not very flat. They're not very precisely thick. I have the other blade in my pocket. So obviously Rask, Fjell, you get the point. After it's been surface ground on the left. And quite a bit thinner too. Because we buy the sheets about 0.156 and we grind them to 1.268. So the question is it flat and is it consistently thick? Variable number one. Typically yes, but there are ways to make bad parts on literally every machine in the shop, whether you're trying to or not. So let's measure this real quick. So we are going for 1.268. 1.267. If I go along the widthwise of the blade and make sure not to hit a burr or a piece of dust, 1.267. If I go on the flipper tab, 1.269, although I might be hitting a burr, 1.265, 1.264, 1.261 by the end, because we do have a bit of taper at the ends. Struggling with that a little bit, 1.255. I don't really care about that because that's where the tabs attach. 1.266. 1.267, 1.268. So literally we're holding about 2/10 on the critical areas that matter. Tabs I don't care about. On the magnetic chuck there's just so little meat here and it's this weak point so it can bend up and just cause problems, but it doesn't really matter. So doing the best we can, holding 2/10 there, that's really good. I talk about this with Saunders quite a bit. I don't actually know how to run that machine. I feel bad that I don't know how to, and I would like to learn, but I've got 3 guys in the shop that are trained how to use it, and it's their job. So Maybe it's one thing I don't need to learn, but I'm quite fascinated by surface grinding, so maybe I will. Okay, variable number 1, stock thickness. It's not 100% perfect, but for our intents and purposes, it's close enough for now. Variable number 2, let's talk about the tool that I use to do that feature. This is a thread mill from Lakeshore Carbide. I've been buying from Lakeshore Carbide for like 15 years. All right, thread mill. Got it? We'll get closer in a minute here. Typically used to make threads. It's a single point thread mill, 0.160 inch diameter. What's cool about this tool is it's a 60-degree V point, so I can come along and I can cut on the top of the part, and I can plunge down and I can cut on the bottom. I can cut the top of the pivot hole, I can cut the bottom of the pivot hole. I can do top and bottom chamfers as long as there's no material left. I can, get around it. Works extremely well. Good tool life for what it's doing. But there's a problem. There's a major flaw. And to show you that, I want to take you to the optical comparator. This is a Starrett optical comparator that I got on like Craigslist about 4 years ago. I think I paid about $800 for it, and it was an absolute steal. Total bargain. Dude, it's got Heidenhain linear scales, glass scales on it, which reads to 20 millionths of an inch resolution. Maybe 10 millionths. No, 20 millionths. 2, 4, 6, 8, yeah. It's absolutely fantastic. It has become one of my favorite manual tools. So what it is, it's basically a green light that shines a shadow on your part, see my finger there, and magnifies it 10 times. I have a 10 times lens in here, that's all it came with. I really want to buy a 50 times lens because I want to blow that up 5 times more. And Starrett will still make me a 50 times lens, but at a cost of $1,300 US, which I would rather keep right now, but I really do want it. It's got an XY stage, so I can move the part side to side, and I can focus it, XYZ actually, and then, up, down, and then Y is your focus. So let's get this part in focus. And you just go till it looks right. You can usually find your crispy focus back and forth a little bit until you find it. Right about there. Then I can come in, and this is a fiber, get the lighting back here. This line is a fiber optic line which senses light to dark. So there's actually a big mirror in the back here that shines the green light through the lens, mirror, back up. And this is a computer that's connected to the linear scales, which literally measures your movement. So if I move the x-axis, boom. If I move Z, boom. And what's really cool is you can use the light sensor to boop, 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 and scan and measure your part. So let's do that. So what I noticed is and I noticed this the hard way, a variation from tool to tool. And since this is a thread mill, we're using both the top and the bottom. Dude, if you're just cutting threads, you don't care about this at all. So I'm using a tool for a purpose it's not designed for, and I get that. And I just really like buying from Lakeshore Carbide, and it's a great, decent price for this tool. And I already have all my programs like using this tool. But there is variation. So if we look here at the V of that thread compared to the end, because when my laser comes in and measures from the end of the tool, what I'm looking for is a relationship between the bottom of the tool and the kind of the crest of the V. And when I designed this tool in Fusion to do all my tool paths, I designed it a certain way, but the tool in real life is different than when I designed it. And the next tool we put in a month later is slightly different. Then the next tool is slightly different, and they wibble wobble back and forth. And if I'm looking for a tooth-out chamfer, this is a huge cause of variation. Okay, real quick, we're going to scan this tool using one of my favorite tools. So I'm going to go over here to the Beatty inspection software. You don't have the best view. There we go. Measure, line, and then it's just looking for 2 or more points to go boop, boop. Let's see, so I'm going to do that first taper. And I'm just scanning around. Oh, it doesn't like it. Let me, new line, that's okay. Start over. Boop, 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 boop. 5 points, good enough. Now from here, I can see my 5 points. And can we see this? The straightness of those 5 points is 4/10. I'm happy with that. That tells me I don't have an erroneous point, I don't have dust, whatever. 4 thou is good. So I'm gonna hit okay, boom, I have a line. Let's do line number 2. I gotta hit the line function. Boop, boop, boop. Straightness of 1/10. Boom, now I have my V. And then let's get the end face. Another line, hit my line. Boop, 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 boop. Bunch of points. Straightness of 2/10. Love it. So, check this out. Now I have a straight line and I have a V. I can hit the point. I can go line to line. It automatically puts a point between those lines. Hit yes, and then I want to measure from line to point. Boom, 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 boom. A horizontal line, 22.9 thou. 22.9 thou. The tool that I have modeled in Fusion, I purposely did this the other day, is 20 thou. Because the last tool that I checked, these just came in the mail, the last tool I bought many months ago was 20 thou. And I was like, okay, let's standardize, let's make it, everything's 20 thou now, based on 20 thou. This exact particular tool is 2.9 thou longer than what I think it is. And we're trying to hit a 2 thou chamfer, boom, blown out of the water, gone. However, now that I know this, I can comp it on the machine when this tool goes in the machine. So we now have a system where when these thread mills, everyone's gonna get checked and measured. This is gonna have a plus 2.9 compensation because this tool is gonna be longer. I might be backwards on that. I gotta do my math. It's gonna be 2.9 thou different than what we're expecting. So it needs a comp of plus or minus 2.9 thou, whatever the answer is. Hard to think while rambling. Anyway, so that's a huge source of variation number 2. I bet you can see why I really like this tool, especially for round parts. When we make parts on our lathe, we can put them on here, measure profiles, measure threads, measure diameters. It's insanely accurate. So I paid like $800 for the thing. I paid, I think, $4,800 for the computer add-on from a local company. They came in, they installed it. That supercharges this thing and just awesome. Super happy with it. I'm a turbo guy, not a supercharger guy. I'm gonna start saying turbocharges. I want to say it's frustrating when other manufacturers, Lakeshore Carbide, not throwing shade, but have a tolerance band that is bigger than my tolerance band, what I'm trying to do with a tool like that. And this applies to other aspects of what we do too. When we are trying to hit such fine, accurate, repeatable, consistent tolerances, we have expectations, we have variables. And when you find differences, it's frustrating. However, this is an excellent way for us to compensate for that variation. We just have to measure it and track it and like be methodical about everything we're doing. Okay, let me think. Variation number 3. Oh, this is a good one. Definitely not using this part of the footage. Are you? This is a really sweet fixture that I designed to hold our soft Fjell blades. Now I've gone through many iterations of soft blade fixtures. For example, in the Kern right now, Rasks are currently soft blade being made on the side of a tombstone. 1 blade per tombstone because it's a 1 knife fixture. The Norseman blades are being made 8 on a tombstone, 2 per side, patterned all around, 8 blades. And that works pretty well. You can see there is a tab here, but it gets cut off. And then that chamfer, I call it the micro chamfer, top and bottom, comes around. Same with the Rask. The tab gets cut off, micro chamfer, top and bottom. You can see the clamp that I have here, the clamp that I have here, and I kind of got it stuck in my head that I want to standardize. That I want to standardize to a same clamp for everything if I can. That'd be amazing. Just make these clamps on the Williman, make the same one for everything. So I came up with this. This is what I call the ultimate blade clamp. Trademark, John Grimsmo. Made of titanium. I've since done my research and realized the modulus of elasticity of steel is twice that of titanium. So basically the bendability of titanium. And this isn't the most rigid, delicate, or super strong thing. It would be twice as strong if it were steel, not titanium. I just happen to have a bunch of titanium. I made this on the Williman from 5/8 round bar. We got a bunch of offcuts, and they're really cool. But they would be twice as strong if they were steel, so maybe I'll do that. Not only do we need a soft blade, like a fixture to hold the soft blades, we need another fixture to hold the finished heat-treated machined blades that don't have a tab. So we need another fixture to hold the finished blades for bevel milling. And then these little ultimate clamps work really, really well there. Love it, love it. I press a 1/8" dowel pin into the bottom, which locates it. So it's located on the pin in a slot and then on the screw, which keeps it, quite located. Not perfect, but enough that the clamp's not just gonna rotate out of the way like our previous clamps did. So that's cool. So I thought I could use this one clamp for hard blades, bevels, hard blade, hard milling on the top, for soft blade milling, whatever. So let me show you what that looks like. Put a blade on this fixture, 2 screws go in to clamp it down, keeping in mind the Robin Renzetti rule that everything is rubber. It reminds me of the Lego song, everything is rubber. Okay, 2 screws, pop, pop. We do torque them. We have this beautiful Sandvik torque wrench set to 9 or 10 Newton inches? No, yeah, Newton meters. No, Newton inches. No. I don't know. Whatever the torque for an M6 screw is. So we torque that, click, click, and then my ultimate blade clamps go right there. Like that. I actually have some older ones that are a little bit fatter, but are actually good to show you guys. Okay, so assuming, put it in, assuming we go click, click, torque, torque, we were making blades like this. 2 at a time, patterned around the middle, so you can just easily make 2 at once. Save tool changes, it's great, it's beautiful. However, those of you who know what you're looking at might notice a couple things wrong with this. First variable we solved was surface grinding this fixture, because we have 3 of these, and they all varied in thickness by a tiny bit, and they all varied in flatness. If I put this in the machine and I put an indicator on it and I sweep it across, it would flow down on both sides and was not awesome. So I had the guys surface grind it. You can see the beautiful finish we're getting. We have this base. I 3D printed that thing. So we have this Aroa base, which lets us, take the pallet on and off. This was able to go right on the surface grinder and allow us to put a fixture. This fixture goes into the Speedio or into the Kern, into the Aroa, pallet changes around, pretty awesome. Now this lets us load it on the bench and on the surface grinder, and it was awesome. So now, even on the machine, these are flat, measure flat all across the entire surface within 1/10, which is amazing. Super flat. Okay, so that variable is now gone. That's whatever number we're on. But the real thing I'm seeing is lifting. The blade is lifting here because we're only clamping it here, 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 and here. This is unsupported. And especially once that tab gets cut off, the back end slightly kicks up. So I'm like, well, dang it. My ultimate clamps are not ultimate. How do I clamp? I was trying to resist making a new clamp. Because making clamps is like annoying. You gotta design it, you gotta make it, you gotta buy stock for it. I was hoping to just use one clamp for everything. I don't know if that logic works. Not enough clamping. So going from water jet stock to machine stock, there's not a ton going on, but I am doing some critical features. The profile has to look really nice. The chamfers have to look really nice. There's a corner rounder, a double corner rounder right there. Jimping, I ream those jimping holes, and the spine gets engraved. I forgot to do this one. So there's, not a ton of operations, but enough that it has to be important. And then a clamp that is going to cover this can't cover any of this important stuff. And then it also has to clear the tool holder that is coming in and doing all these finishing features. Okay, let's jump over to the surface plate. On the granite surface plate, we have our Gorilla stand, which I'm super happy with. Okay, I want to show you guys real quick a couple things. I like the bigness of this Gorilla stand because I can get in here and I can do this larger fixture while also doing tiny stuff. Doesn't have to be perfect, but see there, we're at 0. And being on the Aroa base on here, I can start to sweep across. Oh, I'm off the part. So where the blade sits, I am level, flat, everything to within 1/10. I keep bumping it. Bumping little body here. I should raise it up. But we're just doing a quick little reference measurement right now. Even back here in the corner, pretty much 10th. Super, super happy with that. So I've swept the whole thing. The fixture itself is flat. Okay, now what? What is happening with this blade here? So right where it clamps is where it's probably the stiffest. Even here, what the heck? What is this? What is happening here? No. No. I have 0.6 of variation across this distance. Yuck. Even here, several tenths. Way back here, the screw on that side actually pulls it way down. Oh, because remember the thickness tapers off on some of them, that's fine. But around here, so if I pinch this, I can get it to move a little bit. It kind of just shows super not ideal. Especially here. So there is a variable number 112. The stock is relatively flat, the fixture is relatively flat, the clamping is distorting it in a way. So how do I cover all of that with a mega clamp that goes on top? Let me introduce you to the ultimate blade clamp. I got too much stuff in the way. This bad boy is next level. So a lot of things are going on here. It's thick, it's 4140. It has these extra bosses because literally the tool holder needs that clearance to not crash into itself. All my tool holders are modeled, all my tool stickouts are modeled in Fusion, and I wanted to keep that extra meat for thickness and stiffness and not have this thing be a wet noodle. I didn't do FEA on it or anything. I don't know in the program how it's moving when you clamp it down. I don't really care. I also made this little lip on the inside so that I don't have a blade here. It contacts the blade on the outer perimeter of the blade as much as it can. And not only that, I lapped the bottom. And let me show you why. Okay, so we got 2 clamps. I made 3 of them. One of which I lapped, and one of which is right off the machine. Hear that? It ain't flat. And I'll show you using Gorilla stand. This side, that side's not bad. Oh, if I hit the opposite corner. Whoa. huge warpy. Is it necessary to lap the bottom of my top blade fixture clamp? I don't know, maybe not. It is just another variable that I want off the table. I don't want this, I can't accept that. Yes, it'll deform, it'll whatever, I just don't want it. So let's lap it real quick. I don't do anything real quick. All my videos are long. You like it, I know you like it. Lapping these is a 3-stage process. Could be a 2-stage process. We're gonna make it a 3. Here's our Angus lapping machine. We have a really cool Squadro diamond lapping pad that is stuck onto the surface. And I can come in here and I can hand lap this, just like that. There's diamonds embedded in all these little triangles. And normally when it's running, there's coolant, lubricant that floods on top. I'm not going to do this fully right now, I'm just showing you an example. I'm actually going to have Steve do this tomorrow and finish it up. But you do this for a couple minutes until it's done. I can already see the flats, like the worst parts are starting to shine up. So after lapping on that machine, you would wash off the part to get any loose diamonds off because you don't want to bring diamonds into your measuring equipment. Then you take your trusty Kinetic Precision ground flat stones. Rub them together, because that's just how you do it. Stone your bottom surface. It's not very flat yet, so it sounds gross. What this is going to do, these are non-abrasive. They were abrasive, but then Spencer diamond flattened them on his surface grinder. So all they're doing is cutting down the high spots, polishing the surface, making it really, really, really nice. That will show you the good spots will get really shiny and lapped. The bad spots will stay cloudy still. That'll show you how much work you have left to do. So you would, well, tomorrow, Stephen will lap on that Squadro pad until it's good, and he'll validate with this. And then after that, and he can actually put it on the, back under the Gorilla stand, under the indicator, and you know, make sure, measure the rock. If he's measuring 5 thou, then he laps a bunch, it might be down to 2 thou, and I want it 0 because we can. Last step, I actually noticed when I lapped the first one fully. Doing it that way, I don't know if it's the softness of the pads or whatever with that machine, it ate up these little corners a little bit faster. So we have these cast iron lapping pads that I made that are super awesome. These have 15 micron diamonds, 1, 3, 15, 30, and lubricant. 15 micron diamonds embedded in the top surface, and then I'm not going to do it because I'm not prepped for it yet. Just same thing, this just leaves an even flatter surface. Do that for another minute or two until you're satisfied. Validate, stone it, check it, make sure it's good, and that gets you even flatter. The one thing I did not do on this clamp that I, in retrospect, wish I did is provide some sort of locating feature. I basically just have the 4 screws right now, 6mm screws in 1/4 inch holes, so there's, you know, 15 thou of hole clearance. And I think it's going to clear. I think the tool holders are not going to smash into this thing. But in Fusion, even though it clears in Fusion, if I have 15 thou of slop here, Fusion doesn't know that. So yeah, I wish I would have put a dowel pin, 2 loose dowel pins in the middle. I think it'll be good though. I think it'll be good. So all that work, where does that leave us? I feel like you can read this better on the actual camera instead of on the GoPro. Okay, let's see if I can do this one-handed. Seeing about a 1/10 of variation, maybe not even, in this region. A little bit more as the blade tapers off. Maybe that is something we have to address in this region of the blade. But that's literally the blade tapering from surface grinding, not the fixture. But in here, a 1/10. If I sweep along this top edge, how we doing? No movement whatsoever. Not really, a 1/10. It's awesome. It's awesome, a lot of work put into this. And probably one of the biggest quality of life improvements of having all this stuff figured out and having the tool modeled so that Fusion knows what's actually happening is that the chamfers it simulates in Fusion are accurate, are exact. The little bit of testing I've done so far with comping the tool in Fusion and on the machine so they match, the Fusion chamfers finally match what real life is. I used to kind of be all over the place. I'd be like, well, Fusion looks wrong, but it's right on the machine. No longer. And if you really, really want to know how flat those two features are, we come over here to our optical flats and monochromatic light source. This is a low pressure sodium bulb. You can see it in there. I think it's still warming up. It's not full bright yet. And these are old Russian or Ukrainian optical flats. Got on eBay. They're from like the 80s. And they're fantastic. They're ultra flat. What they do, it's really, really crazy how they work. So I have a Norseman blade here that is my reference standard. And if I can get the light not reflecting, see those stripes? How cool is that? So one of the flattest things in the shop, well, other than my blade, is this gauge block. And look at those stripes. So a set of gauge blocks, they're all lapped super flat. Let me explain. What are we looking at here? Notice how the light is dancing around as I move it. I'm tilting it on purpose. I can get the bands tighter, further apart, twisted, but the point is they're all the same direction, they're all evenly spaced, and they're uniform. And same on this blade, which means this blade is extremely well lapped. Can you see that? I can't see it in the camera lens, but by eye it's insane. It's actually dirt. There we go. Maybe a little bit of curvature to those in this orientation. So I've got a bit of a high spot, but dude, this is so flat. So flat. So what's happening here? The wild thing is that light, the brightness all around us, has a thickness. What? Different colors have different thicknesses. What? So sunlight has a whole bunch of different colors. So it's a whole bunch of different, waves of thicknesses. We've all heard of light waves of light, where it goes like this, right? Well, what's happening in these optical flats, the glass is so flat and the part is so flat that the light is bouncing off of your part and then bouncing off of the optical flat and bouncing. The wave is fitting in there. And how many times it bounces is how many stripes you see. So we use a monochromatic light because it is one color of light. So it is one thickness, 530 whatever nanometers of thickness in this exact color temperature. So we have a very consistent thickness of light wave, and as it bounces top to bottom, every other band is 22 millionths of an inch, or every band is 11 millionths of an inch. So if the curvature of the band from end to end of the part is only one band high, then your part is flat to 11 millionths of an inch. So flat. So anyway, let's take it on our part, see what we get. So put the small one away, open my bigger one, and then I also have a 6-inch one in here. I mean, look at that. Isn't that wild? You have to be very careful not to scratch these. I should not be doing this one-handed. Okay. It's not lapped as flat or shiny, well, not lapped as shiny as the blade, but can you see bands in there? I can see bands. They're not as defined. You see them jiggling? They're not as defined because the part's not as finely lapped. It's 15 micron lap, not 3. So there's deeper scratches. Even though it's flat, the fact that I can see bands means it's flat and shiny, and I can see the bands are pretty linear. And there's not a lot of real estate to really show what's going on. So you have to kind of analyze what you do see. There you have it. It's 1:42 in the morning, and that's when I have time to film videos. Okay, the last step is to actually make a blade. I think I have time to do that right now. It only takes about 10 minutes. I'm gonna make a blade, see how good it works. If everything works, the chamfers should be even top to bottom. It should just work. It should just be perfect. Let's see. You can see in Fusion simulation here, we got the whole kern modeled up. So this is how close the tool holder gets to the clamp. That's pretty close. You can see how I had to keep meat here, and but I had to clearance it, and now I can't change tool holder to a different tool holder because, yeah, it'll work fine. See what I mean about having the thread mill perfectly modeled? So this is based on 20 thou, whereas the current tool in the machine is 19.6, and that tool we measured before was 23.9 or whatever. I just remembered one more variable that's not really an issue on the kern. Thermal. As the machine heats up, as the spindle heats up, as the axis heats up, as the cooling heats up, metal grows. Everything is rubber, everything is thermally, well, most things are affected by thermal. We're actually seeing that and measuring that on the Speedio right now. The Z will grow by over 1 thou, the Y will grow by over 1 thou. Throughout the day, up and down, it swings. The kern, however, is thermally stable. It is chilled. The spindle axis is held to 20 degrees plus or minus 0.1 of a degree. The coolant is currently 20.16. There's a chiller in the back that keeps liquid antifreeze at 12 degrees Celsius, which chills the coolant, chills the axis, chills the motor, chills the spindle, chills. It's awesome. Not a problem on the kern. Here's the tool table on the kern. We have tool 110 is my 160 thread mill, and my compensation is negative 0.2 60 millionths. And that is what this tool measures. So it's 196 or whatever, 194, 1994, I don't know. And compared to the 20 thou that Fusion thinks it is. So. Pallet change, put that pallet in. And since we surface ground the top of the fixtures, they are all three matching, but they're a little bit different now than what Fusion thinks it is. So, probe is going to come in and it's going to measure the surface of each fixture and update the dish. Pardon my French. Holy cow. Okay, that's a problem. That's... Hang on. Can I open the door here? That's a problem. There didn't used to be a clamp there, and I was able to probe between those two other clamps and hit the fixture surface. I didn't break anything, but I'm compressed. And I just moved this. Okay, I stopped it in time. All right, I'm gonna have to probe somewhere else, like here. Not in the middle. I didn't think about that. You don't always think about everything, every variable. All right, that was a close one, but I got it figured out. Coming in, touching the surface, bring it back. If I go into my datum table, it is measuring, the surface of the fixture is measuring negative 2 thou 8/10 below where Fusion thinks it is, which is totally fine. That's my new zero. I don't care. Okay, we're good. We're good, we're machining. Here we got a tiny little 59 thou through coolant drill bit, drilling the jimping holes. Breakage check against the laser. Now change in the reamer. Ream those holes, just makes the finish a little bit cleaner. Looks good. I don't see any rub marks on the side of the clamp, so it looks like the tool holders cleared it just fine. Let's pull it off and see what we get. All right, looking at it, it is 90% there. I'm seeing a very even chamfer side to side, maybe half a thou shifted from where it should be. One side is slightly bigger than the other, so I gotta dig into that a little bit. But I mean, there is an even chamfer all the way around. The only one that's missing is the top of the pivot hole is very chamfered, the bottom is not chamfered at all. I bet you I could see that same thing in Fusion, I just missed it. Yep, confirmed. Big pivot chamfer on top, nothing on bottom. See what I mean about model chamfers are what is actually happening in real life? Big chamfer on top, nothing on the bottom. Fusion is finally accurate to my real life chamfer. I love it. Otherwise, it's actually really good. That is flatter and more consistent and more even than I've ever seen before. Worth it, worth it. That's why chamfers are hard. Does it make sense now? It's like, machining's not hard like it is, but it's just hard to do extraordinarily well. And that's what we're always shooting for. That extraordinary next level, out of this world perfection. Anyway, I'm pretty happy with that. That's why chamfers are hard. I'm John Grimsmo. Thank you for watching. I'll see you next time.